Hi, and welcome to Colligative Properties. When a non-volatile, this just means something that won't easily evaporate. Solute is dissolved in water. The properties of the water change a little bit. Non-volatile solutes include basically things like salt, okay? So things like salt or even sugar, just things that you're able to put into water that we don't expect to come out of the solution very easily. If you put a gas into water, it'll bubble out, so that would not be considered non-volatile. This is something that's going to stay in the water. So it will affect the properties of the water a little bit. Colligative properties are something that are based on the number of particles present, not the identity of those particles. And this is actually something you're extremely familiar with because this is why we put salt on the road in the winter. So this time of year, that's something that we depend on every single day. So a couple of these, there are three properties that we cover: vapor pressure lowering, boiling point elevation, and freezing point lowering. So vapor pressure lowering, what vapor pressure actually is, keep in mind, is it's the pressure of gas above the surface of a liquid, in this case, water. So in order for us to have vapor pressure, like you can imagine maybe some of these water particles, water molecules are evaporating. Once they become a gas, they're going to then create vapor pressure. If we put some ions in here, so if I just kind of jam some ions in here, remember they're going to interact a little bit with some of the different particles. What that's actually going to do for me, that guy down there, once these particles of salt have attached themselves to the water, like this, it's hard for them to evaporate, okay? This is going to actually, because remember, salt is a really high boiling point, like ridiculously high. So when we add salt to a mixture of water, the salt particles are going to be attracted to the water molecules. And because the salt does not want to evaporate, it makes it harder for the water molecules to do so. So those salt particles make it so that these molecules can't easily leave, these molecules of water, and go into the gaseous state because the salt particles don't want to become a gas. So I kind of like to think about this, if you imagine that the water molecules are like balloons that want to float away, the salt is kind of like tying a rock to them. So the general idea here is this: when you add salt, it makes it more difficult for water to go from liquid to gas. Therefore, you will have fewer gas particles, which will lower your vapor pressure. I know that's a lot, doesn't really fit in that box that you have, but generally the idea here is this: salt makes it harder for water to evaporate. Less particles in the gaseous stage, lower vapor pressure. You are not frequently asked about this. You're more frequently asked about boiling point elevation and freezing point lowering. Boiling point elevation actually works a pretty similar way. So when water boils, it's going from a liquid to a gas state. Just like we talked about on that other slide, if we start throwing these guys in here, the salt particles are going to make the transition for water to go from liquid to gas much more difficult. it's kind of like that same idea. Like it's almost like tying a rock to a balloon that's trying to float away. So just like with vapor pressure lowering, by adding salt, the liquid to gas transition for water is more difficult. Therefore, it is going to require more energy to boil the water. So we would have to raise the water to a higher temperature in order to get it to go from that liquid to gas phase. More energy, higher temperature. Freezing point lowering you also need to know. In order for water to freeze, it must align and form a crystal. So if you imagine you had these water molecules down here, maybe this guy's trying to align with this guy. In order for them to freeze, they have to have a connection that forms right there. So as that connection is trying to form, imagine what would happen if all of a sudden one of these guys were hanging out and this guy gets in the middle. That's actually going to block that connection, and that is going to prevent crystal formation. Talk about salting their game. Ha 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 ha. So what occurs here is this. Salt ions block waters from aligning and forming a crystal. Therefore, temperature must be even lower for the crystal to form. So on a winter day, it kind of blocks that formation of ice. It has to get even colder in order for those salt particles, or in order for that crystal to form with those salt ions in there. There are two things to consider. Concentration. If we have a higher concentration of salt, so that could include molarity, percent, parts per million, whatever. Higher concentration of a salt will produce a greater effect. So an even higher boiling point and even lower freezing point. However, there is a limitation to that. For our purposes, higher concentration, greater the effect. Way higher boiling point, way lower freezing point. Number of particles. So when you put in 1 mole, how many particles will it dissociate into? C6H12O6 are same side of the staircase. When this goes into water, it does not dissociate. So this gives us 1 particle per mole. However, if you put salt into water, since it dissociates, what you actually get are 2 particles per mole. So if you had a mole of salt and a mole of sugar and you put them in the same amount of water, you're going to have greater effect with the mole of salt on things like the boiling point or freezing point. So that's why you don't put sugar on the roads, among other reasons. Calcium chloride actually gives us 3 ions when it dissociates, so it breaks into 3 particles per mole. And if we were to dissociate sodium phosphate, we get even more. We get 4 particles per mole. Holy cow. So what's important to understand is if we had 1 mole of each of these, so if we took 1 mole of each of those substances and put them into a liter of water, Na3PO4 would have the lowest vapor pressure, highest boiling point, and lowest freezing point. to the most particles present. One little kind of visual that I like to use too. If you imagine water is usually has a freezing point of 0 and a boiling point of 100. What adding salt or something non-volatile does is it stretches this. Boiling point goes up, freezing point goes down. So it just stretches where water is able to stay a liquid. So a few questions to look at. Compared to a 2 molar solution of sodium chloride at 1 atmosphere, a 3 molar solution, since it's going to have a higher concentration, it's going to have an even higher boiling point and an even lower freezing point. Which aqueous solution of potassium iodide will freeze at the lowest temperature? So you're going to have the greatest effect here. So we're looking for the highest concentration. So as we look through these, we can compare the first two. 1 mole in 500 grams is lower concentration. I'm going to compare 3 and 4. 1 mole in 1,000. So now I'm just comparing 2 and 4. 2 moles in 500 grams of water is higher concentration than choice 4. Number 3, which ones have the lowest freezing point? So I'm looking for the greatest effect there. I'm talking about Ki all the way through here. So this is one substance I'm comparing. Again, I'm going to be looking at concentration. I just looked at these like a ratio. So 10 grams divided by 100 grams. If you do 10 over 100, you get 0.1. 20 over 200 is also 0.1. So that's the same answer. Those are the same concentration. And then the 30 and the 40. So if we do 30 over 100, that would be 0.3. That's a lot of Ki in the smallest amount of water of any of them. And if we do 40 over 200, we get 0.2. Sorry. So our most concentrated, the highest ratio of our solute in solution is with choice 3. Which sample, when dissolved in 1 liter of water, produces a solution with the lowest freezing point? So we want something that's going to break into the most ions. This is an alcohol. This is the same side of the staircase, so this only gives us 1 particle per mole. Lithium bromide is opposite side. It'll break into Li and Br. That's 2 particles per mole. Same side of the staircase. That again is going to be 1 particle per mole. And our calcium chloride breaks into 3 ions, or 3 particles per mole. So the first two have low concentrations, so we get rid of those. The second two have higher concentrations, and also the calcium chloride will give me the most particles, therefore making my answer choice 4.